All right, this is part 4 of the power amps lecture. Now, at the end of part 3, we talked about combining two Class B amplifiers that work together in what we call the push-pull operation. We said there's two ways to do this. We said there's transformer coupling, and the second way was using two complementary symmetry transistors. So I've saved a little time here. I've drawn out, like a transformer coupling first, I've drawn out a little diagram here of a transformer coupled amplifier. So if you look here, we've got a couple things going on. Let's do some labeling. We've got an input transformer. I'll write my labels in red. And we've got an output transformer. We said earlier transformers there's some issues with transformers. They're big and bulky and heavy, and they cost money. So this is one way to do it, though. So let's talk about this way to do it. When size and weight and things like that are not an issue, this is definitely an option that's used. We've got the input transformer, okay? If you look, I'll write down some notes here, what's going on. But we've got, let's write them right here, Q1 and Q2. Even though Q2 looks a little funky, it is a BJT NPN. So BJT NPNs, both NPN transistors. Okay, so, and again, we're just making a few notes here. Okay, we can say the input transformer has a center tapped secondary. If you remember your transformer stuff from last year, that is connected to ground. Okay, so it's a center tap transformer, so there's a center tap on the secondary, and that center tap is connected to ground. And what that does is it produces a phase inversion of one side with respect to the other. Okay, so let's take a look at what that means. Let's blow this up a little bit here. If we're looking at the secondary of the, and I'll write these in, I'll write this side in blue, light blue. If we're looking at the secondary of the input transformer, here's what we end up with. I'm not going to worry about amplitude, but we end up with in phase with the input, top half, 180 degrees out of phase with the input, bottom half. Okay, so we can say the input transformer is converting the input signal, Vs, to two out of phase signals for the transistors. Okay, and I'm going to start writing over here now. Now, because of this, because of the signal inversion, if you look at the way your transistors are oriented, okay, Q1 conducts on the positive part, That's the positive part of the cycle. And Q2 will conduct on the negative part. Okay. The output transformer combines the signals, basically. So what we end up with, I'll draw the output side in red, end up with something like this. Okay, negative cycle. And on this side, we end up with something like this. And our output, full cycle again. All right, so let's take a look at what's going on here. I've kind of drawn the signals here. Okay, so we said because of the signal inversion, Q1 conducts on the positive part of the cycle, and Q2 will conduct on the negative part. Okay, we can say the output transformer combines the signals by permitting current in both directions, even though one transistor is always cut off. Okay. Let's see. What else do we want to say here? I think those are some good notes. Okay. So that's basically how that works. Now let's look at number 2. Complementary. So this is the second method. Complementary symmetry transistors. I should have pre-drawn this one too, but this one uses 2 emitter followers. And both positive and negative power supplies, DC power supplies. Okay, it's called complementary. Because one emitter follower uses an NPN transistor and the other PNP. Which conducts, if you recall, on opposite alterations of the input cycle. Okay, so it's going to take me a little while to draw this one, but I'll draw it as quickly as I can. I want to draw a couple of, I want to draw the positive half cycle condition first. So we've got an input here, call it VN or VS, whatever you want to call it. Okay. We've got a couple of transistors here. I didn't leave myself enough room. I'll draw this one on this page, and I'll draw the next one on the other page. We'll start out with plus VCC here. I'll draw the transistors first. We've got Q1 and PN Q2, PNP. Okay, we set both positive and negative power supplies. So we've got plus VCC up top, negative VCC here at the bottom. Okay, these bases are tied together, and our input comes in here. We'll draw some waveforms and stuff in a bit. Okay, so and our load is taken, our output is taken right here, so we can attach our load RL. All right, there's two conditions. Let's finish off our diagram here. Let's draw our input and our output. So we've got V in. I hate when I do that. All right, let's try it again. So we've got our input. And we've got, I'm going to draw the input with a positive half cycle shaded. I'm going to draw the output. Let's not worry about amplitude, with a positive half cycle shaded. Okay, so in this case, we're in the positive half cycle here. I'll write this part in red. Positive half cycle. Q1 conducting, Q2 off. All right. Now let's look at the negative half cycle. I'm going to go to a new page. Redraw the thing again. So give me a minute. So we've got plus VC, plus VCC. Top here, we've got Q1, we've got Q2. Q1 NPN, Q2 PNP. Output taken here. RL. We've got our negative biasing voltage here, negative VCC. Okay. Bases tied together. Input coming in here. Okay. Output here. Okay, we're going to draw again our signals here. All right. I'm going to shade negative half cycle now. And our output. All we're seeing is the negative side. So V in, V out. Okay. This is the negative half cycle. Okay. Q1 off, Q2 conducting. Okay. So negative half cycle. So this is negative half cycle. So you get a feel for what's going on here. So again, let's jot down a few things that we want to talk about. One of the most obvious things that you see here, there's no DC base bias voltage. So we can say that there is no DC base bias voltage. Okay, so V capital B DC base voltage is 0. So only the signal voltage drives the transistor into conduction. Okay, and this leads to something called crossover distortion. I'll underline that. Okay, so what's going on when the DC base voltage is 0, both transistors are off. And the input signal voltage must exceed VBE for a transistor conducts. Okay, what that does, this causes a time interval. Between the positive and the negative alterations of the input. Okay, when neither transistor is conducting. Okay, so you end up with, let me see if I can draw this now. Good luck with this one. Okay, now I get it. All right, so we end up with something like this. And here's what we have. We have our input looks like this. So this is 0. I'm going to draw another line here. Okay. I'm going to call VB plus VBE, or just VBE, negative VBE. Okay, and I'm going to draw my input. I'll draw it in red. Again, this is not symmetrical. Let's see if I can do this. Not the best, but hopefully you get an idea. Let's erase this little section here. Okay, so what's happening is, I think this works. We only see this. This is what I've shaded in red here is when these transistors are turned on. Okay, and our output and looks like this. I'm going to draw another. So this is our input. I should have said that input. Okay, let's draw the output now. Okay. So what we have, I'm going to draw some dotted lines. I'll just draw them in dark blue here. you can probably kind of figure out what's going on here. I'm just dropping vertical lines when each transistor is on, basically. Again, they have to exceed VBE to be on. So you end up with sort of disconnected humps, I guess we could call them, on your output. And this is your output here. You end up with a hump here. Oh, I was going to draw these in red. On. 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 Okay. So positive hump is going to be what? Q1 conducting, Q2 off. Negative hump, Q1 off, Q2 conducting. Okay, but in between you get these little sections here, 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 and they continue, both Q1 and Q2. Off. Okay, so that's basically your crossover distortion. You get these little bumps with nothing in between, positive, negative, positive, negative. So what you do is you bias the push-pull amp for Class A-B operation. Okay, and we can say that here. To overcome crossover distortion, the biasing is adjusted. To just overcome the VBE of the transistors. Okay, and again that results in a modified form of operation called Class A-B. All right, so and to do that we use diodes basically. So let's add another page and let's draw one here. Okay, so we're still going to use plus VCC and minus VCC. We've still got Q1, which was an NPN, Q2, which is a PNP connected to a negative VCC, biasing DC voltage here. So Q1, NPN, Q2, PNP. Okay, the difference is, I think I left myself enough room here. We've got a resistor, we'll call that R1, a diode, we'll call that D1, another diode, D2, another resistor, R2. Our source goes in right here. It's Vs. And our output is taken same place we took it on the Class B. RL. V out. Vs or Vn. Okay. We can okay, Q2 PMP minus, this is a negative VCC at the bottom here. I'm going to label a point here, point A. We'll talk about that. All right, so what do we want to say? Let's talk about this thing a little bit. Let's write down a few notes. Okay, diodes, D1, D2 are closely matched. To transistors, base to emitter junctions. So the current in the diodes and the current in transistors are the same. Okay, this is called, you'll see this referred to current mirroring or current, yeah, let's just say current mirroring. Okay, so the push-pull stages are biased into slight conduction, even when no input signal is applied, using the voltage divider diode arrangement. Okay, so we can talk about the operation now. Let me jump to a new page. Oops, we will refer back to that diagram. Let's talk about operation. Okay, in the bias path, okay, R1 and R2 are equal value. Same value. Okay, the DC supply voltages are of equal value. Also, one's positive, the other is negative. Okay, this forces, I labeled point A on that diagram, forces the voltage at point A to equal 0 volts and eliminates the need for an input coupling cap. Okay, the DC voltage on the output is also 0 volts. If we assume or let's say assuming both diodes and the transistors are matched, okay, are identical. Okay, the drop across diode 1 equals the VBE, phase 2 emitter junction voltage of Q1, and a drop across D2 equals VBE of Q2. Okay, so and since they are matched, okay, the diode current will be the same as ICQ. So ICQ is VCC minus 0.7 volts divided by R1. Okay, this is for Q1. Let's say ICQ1. Okay, it's VCC plus VC minus 0.7 volts. That's the diode divided by R1. Okay, new page. Okay, and this small, we can say this small current required of class AB operation eliminates crossover distortion but there is a but here, has potential for thermal instability. If the transistor, let's say, if the transistor VB drops are not matched to the diode drops, or if the diodes are not in thermal equilibrium with the transistors. Okay, and a little note here. I don't think we talked about it in our class, but you may have talked about it last semester. We can say heat in transistors decreases base to emitter voltage and tends to increase current. That's all we'll say about it here. But the key here is if the diodes are warmed the same amount, the current is stabilized. But if the diodes are in a cooler environment, they're going to cause ICQ to increase even more. So I'm going to keep them the same temperature. Are warmed, same amount. Current is stabilized. But if the diodes, let's say, are in a cooler environment, cause ICQ to increase even more. So you got to keep them the same temperature, basically. More heat, that we could say, is then produced with more current, say due to higher current. In an unrestrained cycle, in an unrestrained cycle known as thermal runaway. All right. So you can also have one more little piece here before we get into the filter stuff. We used, the two DC biasing supply voltage model, but we can also have a single supply. You may see some of these push-pull amplifier. Just want to talk briefly about this one. So again, we're talking DC supply here. So I'm going to draw it. We've still got the diodes. R1, D1, D2, R1, R2, D1, D2. Okay. Input to Q1. Plus VCC at the top here. Q1 is an NPN. Here's Q2. Q2 is PNP. My arrow is not very well defined on Q2. Q2 is still a PNP. Okay. We are going to put some caps in here now. C1, C2, input goes in here. Yes, output is taken here with a cap in between. C3, and there's our load. Okay, and what we end up with, basically the circuit operates the same way. Let's just draw a couple notes here. We're not going to spend a lot of time on this, but the circuit operation is the same as previous, except bias is set to force the output emitter voltage to be VCC over 2 instead of 0 volts. With 2 supplies. We're talking DC voltage here. So we're talking here, we've got VCC over 2. And here we've got VCC over 2. And we can say, because output is not biased at 0 volts, the capacitive coupling for the input and output is necessary to block bias voltage from the source and the load resistor. Okay. So you can do it with a single DC supply. All right, I'm going to leave this at that, and I'm going to